Hi guys. Okay, so in this video, it is going to be Lewis structures part 2. And here we're going to be talking about kind of some weird cases in Lewis structures and just kind of some exceptions to them. So our first note to make that's going to be really important is that if anything weird happens or anything breaks any rules, it's going to happen on the central atom. So your outside atom shouldn't exhibit any of these like weird rules or anything. It should only happen on your central atom. Okay, so we're going to start by talking about an incomplete octet. So an incomplete octet is when a substance's or compound central atom is stable with fewer than 8 electrons. Now, you already know that happens with hydrogen, and that hydrogen only needs 2 electrons. But boron and beryllium are also exceptions that don't need to be full. So beryllium only needs 4 electrons to be stable, and boron only needs 6 electrons to be stable. So those are 2 of our exceptions to this rule. All right, so now let's go ahead or the 2 other exceptions beyond hydrogen. So hydrogen only needs 2, beryllium needs 4, boron needs 6 to be stable. All right, so let's go ahead and do a practice problem here. So we have boron triiodide. So first off, we have boron. We need to write a formula. This is a covalent compound, so boron is B. Triiodide would be 3 iodines, so Bi3. All right, and we're going to figure out our valence electrons. So we have boron. We have 1 boron, and boron is in group 13, so that means it has 3 valence electrons. Then we have iodine. We have 3 iodines. Iodine is in group 17, so it has 7 valence electrons. So 3 plus 21 gives us a total of 24 valence electrons to work with. All right, so I'm going to go ahead and take boron, put it in the middle, and bond 3 iodines around it. All right, so at this point I've used 6, so I still have 18 left. So first things first, fill our outer octet. So 2, 4, 6. The iodine is full. 8, 10, 12. The iodine is full. 14, 16, 18. The iodine is full. Okay, so let's check how that we've used all of our electrons. 2, 4, 6, 8. Iodine's full there. 10, 12, 14, 16. Iodine's full. 18, 20, 22, 24. All right, so I've used all my valence electrons, and all of my iodines are full with those 8 valence electrons. Boron only has 6 around it, but because it's one of our exceptions, it only needs 6 to be full. So this would be the correct Lewis structure right here for this one. Okay. Let's do beryllium chloride. So beryllium chloride is actually technically an ionic compound, but it does bond more like a covalent compound. So to figure out its charge, we have beryllium, which is Be, the positive 2 charge, and then we have chloride, Cl, the negative 1 charge. So we swap, drop, reduce. We end up with BeCl2. Now, the reason it bonds like this is because the difference in electronegativity is not great enough between beryllium and chlorine for beryllium to completely give up its electrons. So even though technically we would consider this an ionic compound, it's going to bond closer. In reality, it's actually closer to covalent in the way it bonds, but just because of there's not a great enough difference in the electronegativity. Okay. So now that we have that, we need to determine our number of valence electrons. So we have beryllium, and we have 1 beryllium, and beryllium is in group 2. That means it would have 2 valence electrons. We have chlorine. We have 2 chlorines. Chlorine is in group 17. So it has 7 valence electrons. So 2 plus 14 gives us a total of 16 valence electrons to use. All right. So we're going to put beryllium in the center, bond our chlorines to it. We've used 4, still have 12 more to use, so we're going to fill our outer octets first. And I've used all of my electrons. And chlorine, both chlorines have 8 valence electrons. And beryllium here only has 4, but beryllium is stable with 4, so this would be a correct Lewis structure. Okay, so that is an incomplete octet, so it has fewer than 8 electrons. Now let's look at an expanded octet. So, opposite of an incomplete octet, an expanded octet is stable when it has more than 8 electrons. And this only happens in the 3rd period and below. So this only happens in the 3rd period and below. All right, let's jump in and let's see what this looks like. All right, so right here we have phosphorus pentafluoride. So I have phosphorus, P, and then pentafluoride, F5. All right, well, let's determine our valence electrons. So we have 1 phosphorus, and phosphorus is in group 15, so that means it has 5 valence electrons. And then we have 5 fluorines, and fluorine is in group 17, so it has 7 valence electrons. So 5 plus 35 gives me a total of 40 valence electrons to work with. Okay, so step 1, take our central atom. It's going to be phosphorus. And we're going to go ahead and bond our 5 fluorines to it. So 1, 2, 3, 4, 5. Or 5 fluorines. All right, so at this point I have used 10 valence electrons, so I still have 30 more to use. So I'm going to go ahead and fill my outer octets. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Yay! So I've used 30 now. So everybody has a full, all those phosphoruses have a full, sorry, not phosphoruses, fluorines have a full octet. And then phosphorus has 2, 4, 6, 8, 10. Now again, because it's in the 3rd period, or 3rd row of our periodic table, it can actually hold all 10 of those electrons. And so it would be stable because it does have at least 8 electrons around it. So it is stable because it has more than that, so it's still stable. All right. Okay, let's do the next one. ICl4 -1. All right, so let's determine our valence electrons. So I have iodine, 1 iodine, and it's in group 17, so that means it has 7 valence electrons. Then I have chlorine, 4 chlorines, also in group 17. And then it's -1, so that means I'm going to add 1 extra electron because negative tells me that I've added 1. So 7 plus 28 plus 1 gives me a total of 36 valence electrons to work with. All right, I'm going to put iodine in the center. Go ahead and bond my 4 chlorines around it. I've used 8 valence electrons at this point, so I still have 28 more to use. So let's go ahead and start adding them on. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so now all of my outer octets are full, but I still have 4 more electrons to use. So anytime we have extra electrons and our outer octets are full, we put them on the central atom. So we'll go ahead and put those on the central atom, our extra electrons. And then we put it in brackets with the -1 charge. Everyone has a full octet. Iodine has an expanded octet, but that's okay because it's below the 3rd period on our periodic table. All right. I'm going to do one more with you guys, and then I'm going to leave one for you guys to do here. I'm going to do xenon tetrafluoride. So xenon is Xe, and then tetrafluoride would be F4. All right, let's determine our valence electrons. So xenon is a noble gas. So we have one xenon. It's in group 18, so it has 8 valence electrons. And then we have 4 fluorines, and each fluorine has 7 valence electrons because they're in group 17. So 8 plus, 28? 8 plus 28, 36 valence electrons to use here. All right. So we're going to put xenon in the center and go ahead and bond the 4 fluorines around it. All right, so I've used 8 valence electrons, still have 28 more to go. So let's start counting. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we saw 4 more electrons, so we're going to pop them on our central atom. And this one is not charged, so it does not need to go in the brackets. And that would be our Freynes-Lewis structure for xenon tetrafluoride. Okay, I want you guys to try to do this one right here, ASBR5. So pause the video and try to solve this problem, and then come back to the video when you're ready. Okay, hopefully you completed that problem. I did, and this is what I got as my final Lewis structure for ASBR5. Okay, guys. Oh, whoa. So the last exception, or kind of weird case that we're going to be talking about, is resonance. And resonance is when a molecule can have different structures. So typically in a resonant structure, one of them is a double bond and the rest are single. Okay, so let's work this one out. All right, so we have the nitrate ion here. So nitrate is NO3 with a -1. All right, so we're going to go ahead and solve for our valence electrons. So nitrogen, there is 1 nitrogen, and each nitrogen will have 5 valence electrons. And then we have 3 oxygens, and each oxygen will have 6 valence electrons. So add that up, 5 plus 18, give us 23. Yeah, 5 plus 18, 23. And then there's a -1, so we need to add 1 more. So that gives us a total of 24 electrons to work with. Okay, so I'm going to go ahead and put my nitrogen in the middle and bond my 3 oxygens around it. 1, 2, 3. All right, so at this point I've used 6 electrons, so I still have 18 more to use, so we're going to fill our outer octets. So 2, 4, 6, that oxygen should be full. 2, 4, 6, that one is full, and 2, 4, 6, that one's full. Okay, so at this point all of my oxygens are full, but we can see that my nitrogen only has 6. So we don't have any more electrons, so what we're going to do is steal a lone pair from one of the oxygens and make it a double bond. And so then everybody has 8, everybody is full, and that would be correct. However, I didn't have to take it from this oxygen. I didn't have to take it from this oxygen and make the double bond there. I could have made the double bond somewhere else. So whenever we do resonant structures, we have to basically draw our double bond on all of the oxygens. Since it could potentially be on any of them, we have to draw it on all of them. And what actually happens in a resonance is that it's more, instead of being like one, instead of being, one double bond and 2 single bonds, what really kind of ends up happening is that you have somewhere in between. All of them end up being kind of hybrid bonds that aren't really double or single. So they're somewhere in between. So yeah, so we would draw all 3 of our resonant structures anytime there are multiple. So it really happens, again, when you have 1 double bond or 2 double bonds even and 1 single, and it leaves you with like extra possibilities of where else it could go. You do need to draw out all of the resonant structures. Okay, so I'm going to do 1 more of these with you and then leave you guys to do the last 2 on your own for practice. All right, so this one is carbonate, and carbonate is CO3 with a -2 charge. So we have carbon. We have 1 carbon, and each carbon has 4 valence electrons. And we have oxygen, 3 oxygens with 6 valence electrons, and then that -2 tells me to add 2. So I have 4 plus 18 plus 2 gives me a total of 24 valence electrons. Okay, put carbon in the center, bond my 3 oxygens to it as far apart as I can. I'm going to move this up a little bit so that I have a little more room. Oh man. Come on. Struggling with my drawing here. Okay, so I've used 6. I still have 18 to use, so I'm going to fill up my outer of my oxygens. So there's 6, 6, and 6. So I've used all 18 of my valence electrons now, and I can see all my oxygens are full, but my carbon isn't, so I don't have any extra electrons, so I'm going to steal a pair and make a double bond. And then once again, because one of those is a double bond, and there's really no reason I did it on the oxygen instead of anything else, I am going to go ahead and draw out all of my possibilities of the double bond on all of the different oxygens, since it could really be on any of them. I'm going to draw out all of my structures. And there we go. I have all of my resonance structures drawn now with the bond on all of the oxygens. Okay, I want you guys to try to do the nitride ion and ozone on your own, and then so pause the video now and then check back in a few seconds. Or I guess restart it when you're done, and we'll go over them. Okay, guys, hopefully you are done. These are a little easier because they both only have 1 double bond, so you just have to draw 2 Lewis structures there, basically with the double bond oscillating, and this is what they should look like. All right, guys, I hope this video was helpful. Feel free to email if you have questions, and we will definitely go over some of this next class as well. All right, bye, guys.